Thank you very much. Thank you to the faculty of DPRI for this great honor. I've encountered many distinguished scientists and others on my past visits here to DPRI, and I know that you must have many choices of possible people to select for this honor, and I really appreciate that you have seen me as worthy. In fact, this honor means so much because it comes from you, the Disaster Prevention Research Institute. Disaster prevention is your vision, and it's also my vision. And we share a vision to use our talents to care for the welfare of others. And so this is a community of with a shared vision, and I appreciate it very much. My topic for today is seismic hazard analysis, and I will have an emphasis. I see. Yes, okay. I will put an emphasis on what the critical questions are that still need to be answered. We've made much progress together, but there are still a number of critical questions, and what I'd like to do is put some emphasis on what these critical questions are. So I'll start with this slide. It shows the 2014 National Hazard Map from the United States Geological Survey. I've had the privilege in the past several years to be chair of a committee that is an external committee to help the USGS with developing this map, improving this map. And as a consequence of that opportunity, part of my, this is informed very much from that experience. So to build that map, as all of you would understand, we start with hazard curves. And this is an example of a hazard curve for Reno, Nevada, where I come from. And so the horizontal axis is peak acceleration, and the vertical axis is the annual exceedance rate. And then there is a horizontal line, and we pick the point on that line where it intersects the hazard curve. And this point on the line becomes one point on the National Hazard Map. So in order to build our National Hazard Map, the hazard curve is at the heart of everything we do. And models are required to estimate the hazard curve. To set up these models, then, this is an example for the Reno area where we have active faults and we have historical earthquakes. And so the conceptual process to build this hazard map is to estimate the magnitude and the strength of shaking from each possible earthquake source. We also have to estimate how often each of these earthquakes occur, and then we add up all the sources. So that is the conceptual basis. Now, what I plan to do is to identify 15 key problems that need to be solved at the present time to improve these seismic hazard studies. For some, I don't have time to do more than to just define what the problem is, and for others, I'll go into a little bit more detail. And I hope this won't put you to sleep. Last night when I was practicing this talk, it put my wife to sleep. And so I hope I'll do better today. And I need to credit many people here. My, thank you. My, there are many colleagues here that have contributed to the different parts of the research, and many colleagues back in the United States. And my wife has always been a wonderful supporter of everything that I have done. So to build this hazard curve, then, we have two different parts. We have to describe the seismicity model, and then we have to describe the ground motions. And so the seismicity model, we have two different parts. We have the faults, which would be indicated over here, or we have the historical earthquake activity. And to describe the historical activity, the first thing is to decluster the catalog. And the reason for declustering in the United States is to make the catalog Poissonian. I've put up here the question, should it be declustered, and if so, how? And assuming that we are going to do it, the declustering process is not unique. And so the first problem that I would identify is, what is the criteria that we should use in order to go about this declustering? And I think it needs to be an interaction of seismologists and engineers. The second, and so that's all I'll say about that. The second question is, what is the magnitude frequency distribution for a network of faults? So we have different earthquakes. How large and how frequently do earthquakes happen there? And I have a couple of slides that will illustrate that, so I won't read these words. Here is an example of some of the faults in the vicinity of Reno. And let's just consider this one on the top in green. It's 36 kilometers long. It has a dip going underneath the city of Reno. It has a width. It has a slip rate. So our process will be to use the length of the fault to estimate a magnitude, and then from that go to a moment, and then to an average slip, and then use the slip rate to come up with a rate of the earthquakes that we have for that particular fault. Okay, so that is the current procedure in much of the United States. It's a little bit different in California. I'll get to that momentarily. But the problem is that this model is too simplistic. And I realize this is a rather poor figure, but it comes from a paper by John Caskey and others describing the 1954 earthquakes in the Reno area. This is the last set of magnitude 7+ earthquakes in the state of Nevada. And what it identifies is that during this Fairview Peak and Dixie Valley earthquake sequence, a large number of faults were involved, not just one. So, and also there were a number of smaller earthquakes on the fault system. So the idea of defining a single maximum, full-length rupture earthquake is overly simplistic. And we need to have some system that is more inclusive of the rupture models. Now, in California, in the latest version, they used a model which is called USURF-3, where they subdivided faults into subsections and then looked for all of the possible combinations of subsections. For this fault system, I've given an example with the black lines, if you can distinguish them from the other colors, showing several different possible ruptures, and then try to find the rates of each of these possible ruptures. The problem with this approach is that the solution is extremely highly underdetermined. So I think we need a better way. And so in terms of dealing with a network of faults, this is the second problem that I would identify as an important one for us to try to solve. The third one, and I'll just mention this briefly, is how deep into the crust do continental earthquakes actually rupture? The plot shows the rupture length on the horizontal axis and the depth on the vertical axis of a subset of large strike-slip earthquakes. And so you can see that there may be some depth dependence, and we don't really know what that is. My fourth problem is, currently in the West, and here in Japan, I think you can do this also, we estimate the rates of earthquakes from slip rates of faults or from strain rates. But we need other methods, especially in the eastern part of the United States or other areas with lower seismicity rates. We don't really know what controls the rate of earthquakes. And so this method that we use of constraining the rates of earthquakes based on the strain rate or slip rates just doesn't work. So we need to have a better way of doing that. And even in active areas like California, we need to quantify the off-fault strain rate because we, how much of the total strain occurs on the active fault, how much is someplace else. So these are, that is a fourth important problem that I see for looking at the seismicity. Now, I'm going to jump now to looking at the other half of the input to the seismic hazards, which is the ground motion models. And with the ground motion models, we have two different aspects. We have the ground motion prediction equations, or we have synthetic seismograms. So we have these two different approaches. Ground motion prediction equations, this is one example of a model by that on the horizontal axis we have a distance, on the vertical axis we have peak acceleration and different lines for different magnitudes. And so let's look at the issues associated with those first. Now the first issue is this question: what's the ground motion very near a large magnitude earthquake in the continental crust? And the problem is that there just isn't enough data and the events are rare. So here, for instance, is a representation of distance and magnitude of all of the earthquakes in the data set that was used to generate the latest ground motion models for the western United States and other continental regions. So a log scale for distance, magnitude, different colors for different levels of ground motion, but the critical area is magnitude greater than 7 and distances, say, less than 10 kilometers. And so that area, that is blown up over here. And you can see that there just aren't very many points there. We need more data. And, what more can we say? We need more data. A part of the problem is that these events are fairly rare, okay? Without going into all of these details on the source of these plots, just say that for strike-slip earthquakes, for instance, a magnitude greater than 7 earthquake in a continental area is only happening maybe once every other year or so. So every time a large earthquake of this nature occurs and we don't get data, in a sense it's a setback for all of us who are concerned with the seismic hazard. We really need to be paying attention to more ways, more innovative ways to gather data from these earthquakes that are the most critical for the hazards in our urban areas. And then when we do get an earthquake, we have to make sure that we avoid the mistake of thinking that this earthquake that we did get is typical. So for instance, I was involved in collecting this strong motion record from a magnitude 8 earthquake in Mexico in 1985. And this record was a magnitude 8 earthquake, and the station was right above the fault. And so we thought, well, okay, could it be that this record, and it was an old kind of instrumentation, so that the instrument turned itself off and then back on again after a short gap. But, you know, you're right up, here's the map of the area. The station is right there at the top of this pointer, right in the middle of this, the aftershock zone. And so it seemed, you know, maybe magnitude 8, magnitude 9. A big factor between the two is that how far the fault ruptures. And so maybe one temptation is to think of this as representative of what a great earthquake might do. But then your earthquake happened in 2011 in Tohoku, this great disaster here. And this being right above what you might call the strong motion generating area, this record is maybe 4 times as far from the strong motion generating area, and it's already twice as big. So this would be telling us, just as a reminder, that we need to be cautious about thinking that one earthquake is going to be representative of what the motion is. We need lots of data, not just 1 or 2. Okay, let's see. So another question with the ground motion prediction equations is, how should the site conditions be represented? Okay, so 30 years ago, we were just using qualitative descriptions. It's soil, hard soil, soft soil. Now VS30 has become a proxy for the site response for many of the GMPs. But I think we need to find ways to do better. And I have a couple slides to illustrate that. So here we have magnitude 6.5 to 7 earthquakes in the database that we use for the Western U.S. And the black dots on both sides represent the soft sites, and the red dots represent the relatively hard sites. Okay, and on this side, the red dots are plotted on top, and on this side, the black dots are plotted on top. So, so the data on both sides are equal, but this emphasizes that, yes, there is some difference between the sites with a low VS30 and with a higher VS30, but it's not a huge difference, and there's still a lot of scatter. So, and the scatter in these points is measured by a quantity called sigma that I'll mention again later. So, so you can see that these VS30 is not doing a particularly great job of separating the two. And so we need to do better. I have another example of that, and that's from an earthquake I've been looking at, or the sequence with Professor Kawase-sensei here. And so this is a magnitude 6.7 earthquake in 2011, normal faulting. And complex 2 different faults involved, and of course a great set of data from KNet and KICnet. And so just as a reminder, this is an iconic picture of normal faulting in my state, in Nevada, from the Dixie Valley earthquake in 1954, and here's some of the normal faulting from this 2008 earthquake here in Japan. And so now, based on VS30 or estimates of VS30 for the stations here, the hardest one, so here, this is showing all of the peak accelerations recorded in these data sets, and here we have the hardest sites, which are showing up having lowest ground motions, and then a range of somewhat higher values and a range of higher values. And let's see, these are the hardest, somewhat lower values, even lower values, and then the softest sites, which are showing up at the top over here. Okay, so we can see that VS30 is having an influence, but still I think we need to look for ways that we can do better to distinguish the sites than just VS30 alone. So I consider that an important problem. The related question is, can this parameter sigma be reduced? It plays a critical role for PSHA results. And so here's an example of the role that it plays. The solid line over here on the right is showing, well, essentially peak acceleration and the exceedance rate for this site called Lovejoy Buttes, which is in the Mojave Desert of California, north of the San Andreas Fault. And so here's the San Andreas Fault coming through like that. Okay? So this site is just 15 kilometers away from the San Andreas Fault. In fact, there's the fault in the background of this figure. And here we have some rocks that look like they're somewhat precarious and could be knocked over if we had strong enough shaking. And our hazard model over here, so this is the peak acceleration we expect to knock the rocks over. And the age of the rocks, these rocks, it's a very dry area. We believe those rocks have been essentially intact for the last 10,000 years, since the end of the last glacial period. So a probability of 10 to the minus 4 and the peak acceleration that will knock them over. And this is, our hazard model is saying that the ground motions should have been strong enough to knock them over. You know, that at this rate we should have ground motions strong enough to knock them over maybe 10 times in the lifetime of the rocks. So there's a contradiction there. And if for some reason we thought that sigma was substantially smaller, then that could reduce that inconsistency. Okay, let's see. This is another example. Well, but I'll just focus on this one. Well, no, I won't. So here we have the peak accelerations that you saw previously for the 2011 earthquake in the Fukushima area. And so you can see all of the scatter that we have here. And at this time, they are being compared with the ground motions from 4 models that we're using in the western United States. These don't have any corrections. These use the corrections of Kawase and Matsuo to adjust all of them to a fixed value of VS30, and there's still a lot of scatter. Now, when we do our hazard analysis, we are typically making an ergodic assumption that says that sigma measured from the scatter of these points is well, that's how we characterize the uncertainty, and that's obviously a spatial scatter. It's resulting from points located at many different locations. But when we do the hazard analysis, we're trying to find the hazard at a single point. And so using the spatial distribution of the scatter is the wrong thing to do. So the corrections of Kawase and Matsuo are, in a sense, going in the right direction to eliminate or minimize the effect of this ergodic assumption, this incorrect ergodic assumption. And they're essentially equivalent to what some other people have called single station sigma. But even in this case, sigma is too high. It's too high for the precarious rocks that we were looking at. So we still have work to do to figure out how to solve that problem. Okay. And one other question then related to GMPEs, how do we adjust these models for differences in the regional geology and tectonics? Okay. So, for instance, these are now, these are the residuals, so the observations corrected for using the Kawase and Matsuo corrections, corrected as a function of distance for these different stations. And these are residuals from one of the models that we use in the western United States. What we're seeing is for both peak acceleration and peak velocity, the residuals are increasing with distance. Okay, they should not be increasing with distance if we had the same velocity model, the same Q structure in the two regions. So so our issue is how do we adjust from one region to another in order to take advantage of all of the great data that you are collecting here in Japan and apply it to solve problems in regions where we don't have nearly as much data. Well, okay, this is just a different way of addressing the same problem where we're, so I can pass over that. The other approach to generating our to ground motion estimation is synthetic seismograms. Okay, and we can ignore that equation here. But one of the issues is how should we model the seismic source? Okay, so here we're going to be focusing on the spectrum of the source. There are, of course, time series and other issues. But let's focus on the time series of the source. And what we see here, well, this is just a sample of one seismogram, but let me see, what do I want to do? Here we have a seismogram recorded at one of the kicknet stations, and so we have the surface ground motion and the downhole ground motion. And what we see here is downhole, the spectrum is relatively flat, whereas at the surface there's this huge peak. So can we say that the source spectrum is relatively flat, omega squared, or not? Now, the Hiroshi Kawase's lab has been working on a number of methods to characterize the site, and for this particular site, their models would be predicting this sharp peak here at that particular station for the amplification of the ground motion at the surface. And so if you look at the shape of that peak compared with the shape of the observations, there's a fair bit of agreement. This line is just offset downwards for clarity. So, so this might suggest that the source spectrum itself could generally be considered to be flat, and, and what we would call omega squared, where the acceleration source spectrum is flat. But there's another issue. So there's a parameter that I called kappa that characterizes a sort of a first-order fit to the shape of the acceleration spectrum at high frequencies. And we might be able to explain this parameter entirely by wave attenuation, but statistically, when we look at it, there are some cases where the variability in the measurements of this are much better explained using a source term. And so if there's a source term involved, then that would indicate that omega squared is not the correct, or not always the correct model for what is for the high frequency source spectrum. So why is it variable, and does it imply that we don't really know what the source, don't have a consistent model for the source spectrum? Okay, two more related to synthetic seismograms. Can synthetics can they do better than the GMPEs? And so this is a question. There's a lot of research going on with this question. And there are many different approaches to synthetic seismograms, and our colleagues at the Southern California Earthquake Center have a project going on to see how good we can model the synthetics. And so the question, can they do better than the GMPs? One would think that if you put more physics in, you should be able to do better. And the related question, because site response is so important, how effectively can the site response be represented in the synthetic seismograms? And so I'll illustrate the two of those questions together. So, well, this is a method that I'm using to generate synthetic seismograms, and I don't want to go into those details. Here's an example of data on synthetics, accelerations for 3 components, velocity for 3 components, displacement for 3 components for one of these earthquakes in the Fukushima area. And so you can see that at least some of the time the seismograms can kind of look realistic. This is showing the residuals. So if we take the synthetics as our model, and then we find the ratio of the data over the model in the spectral domain, then each line here is the residual for one of the 40 stations that we're using to study this. And then the black line is the average of those. And so this would seem to be suggesting that we can calibrate our ground motion synthetics to give the same answer as the data, even if the GMPEs are not giving the same answer. But when we look at sigma for those models, so the sigma corresponding to that is up here, and for the response spectra is over here. And when we look at sigma for the for GMPEs, the sigma for the GMPEs is lower. So that means we still have a ways to go in order to get our synthetics there. But it would seem like using more physics than the GMPs, we ought to be able to do better. Okay, so that's the end of the ground motion issues. I'd like to bring up some general issues as well. Okay, so our hazard maps don't show the uncertainties. Now we know, I've just been talking about different uncertainties in a sense in the ground motions, and so the hazard maps don't show the uncertainties. And so because of the uncertainties, from one generation of hazard maps to another, we might get different answers. Like here in Reno, we have different answers for the hazard as a function of 4 different generations of the USGS models. Are these differences significant? How do we answer that? And I'm going to just sort of skip over those in the interest of time, and they're really getting to be details. But perhaps there's a way to define an uncertainty in the mean of the hazard that would look, where that would answer the question, how much uncertainty should we really be dealing with? And so by this approach, perhaps there is some sort of a way, something like this or some other, where we can define an uncertainty in the hazard that would make sense to report to the engineering community as this is the uncertainty that we're dealing with. The second general question that I think we need to resolve is, how can the hazard maps and the hazard curves be tested? Because we're dealing with uncertainties that are way down, we're dealing with ground motions that are happening over thousands of years, and so we can't verify them experimentally. Precarious rocks in a few places might tell us if we're doing things right or wrong, but we don't really have a good way to test them. And the other thing is that I don't think we as a community can answer the question, what constitutes failure? There are some people who would look at a hazard map, and if an earthquake happens and it causes higher ground motions, they'd say, oh, the map failed. There are other people who would look at that and say, well, our hazard map is representing a compromise where we are agreeing that we don't want to put infinite resources into protecting our society against every possible extreme earthquake. So we make this compromise. We choose a hazard level in the U.S. 2% in 50 years. And so then when an earthquake happens and it causes higher ground motions, we just say, well, okay, that's just, that's expected that probabilistically some of the time we're going to have higher ground motions. And that's part of the trade-off that we're making in balancing society's resources. So we don't really have a common ground, a common understanding of what constitutes failure of these hazard maps. And I think that we need to be thinking about that question. And then this last point, and I have to apologize for all the tiny writing on this one, but the last question is, are we doing the right thing? Just overall. Do we need to change our practices in any fundamental way to achieve greater resilience? And what motivates me to put this question up is that in the U.S. we just reauthorized the National Earthquake Hazard Reduction Program. And in that reauthorization, which was very heavily influenced by engineers in the Earthquake Engineering Research Institute and seismologists in the Seismological Society of America, the findings inside of that reauthorization record that the United States is not prepared to remain operational or to recover from a large earthquake under any specific schedule. And so the purpose of the NEHRP, the National Earthquake Hazards Reduction Program, was expanded to include increasing our resilience, the resilience of communities, and to point out the need to develop new planning codes along with the model building codes. And it calls for a full review of the program, and that review is expected to lead to the development of a new generation of functional recovery codes and standards for all of the components of the built environment. So this is a fundamental question of seismologists and engineers working together, and not just those, but the full earthquake professional community, to characterize, answer this question, are we really doing the right thing? Okay, so I could summarize by reading through the key questions, but I think you have abstracts there that, well, one of the questions, the wording has been changed a little bit, but you have those in your abstracts, and so I don't need to go through those. And so I will just close by saying that we need to work together to solve these questions, with the end of the word questions missing for some reason here. So I'd like to thank you very much. I'd like to thank you for your attention today, thank you for the very generous recognition that you've just given me. Thank you for welcoming me so many times to come to DPRI over the past years, and thank you for collaborations and friendships over many years of my professional career. So thank you all.
Thank you very much. Very wonderful memorial lectures, presentations. 少し時間がございますが、もし何かご質問等ありましたら挙手いただければと思いますが、いかがでしょうか。Any other? OK。じゃあよろしくお願いします。マイクはありますか。
John, congratulations and thank you for your great presentation. I have a question about the list of your questions. Is this the order of the list tells us that which question is more how do you say which question is to be solved in this order, or is it in random order?
Yes. No, the order has nothing to do with priority. There are many different talents here in this room and elsewhere, and so we need to make parallel progress on all of them. This has nothing to do with priority. It was in the order first to be somewhat systematic, source, and then ground motion prediction, and second, the order that came to my mind and that seems to make sense in a presentation. And I do not claim that this is the only list or the best list. I'm sure that there are other questions that are equally important that I left off. So it's just a list that I put together for the sake of this presentation, informed by my experience. So thank you for the question.
はい、ありがとうございました。他にございますでしょうか。よろしいでしょうか。よろしい。じゃあただの先生。マイクいきます。
Resilience
Well, I'm not quite sure how to answer this. I think EERI is committed to international collaborations, and to the extent that I've been chosen to be on their board, I've certainly been promoting international activities. We can do better, and I think that I think that this upcoming review, there is going to be lots of opportunity. Let's see, especially in the full review of the program, I think that there's going to be lots of opportunity for many different voices to put in their input. So it's not just going to be the engineers who are closely involved in earthquake engineering problems in the United States. I'm not sure. Did I answer your question?
I think it's regular in Japan also. We have various areas of the issue related to those engineers. So maybe one of the some points for us to refer, and if you can straight to us, it would be also very interesting. But anyhow, I'm very much encouraged that you said that this process is open for me. I mean, other was part of the work, so we would like to contribute.
I will carry that message.
はい、よろしいでしょうか。それではそろそろ時間になりましたので、以上をもちまして、アンダーソン先生の、記念講演を終わりたいと思います。Thank you very much, Congratulations, DPRI Award.